So TCP is the most reliable way for two machines to talk to each other over the network. The real question is, how is one web server able to handle and serve multiple TCP connections? In this video, let's understand this by building our own server from scratch using raw sockets. And while doing so, we will understand system calls, socket programming, their limitations, and then we tune our approaches to handle multiple requests at once. So let's jump right into it. So we all know TCP, most reliable way for machines to communicate to each other, and the logical entity that wraps the entire thing around communication is called as a socket. We typically see connections to be of two types, TCP connections and UDP connections. In this one, we'll focus more on TCP, but UDP is very similar to it. It's more about the guarantees that each one of them brings in. TCP, more on the reliability. UDP is more about basically fire and forget. You can read more about it on Google. So let's start with the most fundamental question. What exactly is a TCP server? So to put it in a simple terms, TCP server is a very simple process that runs in a machine that listens to a port which understands TCP, right? So for example, I can start an Apache Tomcat server. I can start a Spring Boot server. I can start a Flask development server. I can start any server which listens to a particular port. Anyone who wants to talk to this machine has to communicate over this port. That's the semantic, right? Okay, so if we want to write a TCP server from scratch, what exactly would we need? We would have to start a process, which is typically what we do, go run something. And then we have to listen to a particular port. So let's start with this, right? So here I'm starting from an absolute scratch. I have no code written. I'll start with creating a simple file, main.go. The entire demonstration will be Go based, but you can pick your favorite language to implement, right? So we'll start with this simple thing. So we'll start with package main and then func main, within which I'll write fmt.println and I'll write hello world, right? This is a very simple hello world program in Golang. So I'll do go run main.go and we can see hello world getting printed on the console, and it did, right? So our Go is very much set up. So what do you want to do? When our process starts, basically what we are writing is we're writing our own TCP server. So when this TCP server starts, we want to listen to a particular port. So in Golang, there is a package that does that called net. So when what I can do is I can do net.listen. And I can pass in that, hey, I want to listen for the TCP protocol on the port 1729, which is what I'll do, right? So when I write net.listen TCP, and then the second argument I pass which port I would want to listen to, it means that I'm like, this process is now reserving a port 1729, right? So now I can just run main.go and let's see what happens. Nothing actually happened. The program started and program finished by printing hello world. So did it even do anything? It did. It actually, when the process started, it actually reserved this port for this process. But because we did not do anything after that, it just released. It just killed, right? Because it just successfully returned, right? Okay. So now what do we want to do? Let's see the return value of listen. So listen returns an error and a listener, right? So what we'll do, I'll just accept this. I'll say listener and error. And in case there is any error, we'll just do a fatal right now. If error not equal to nil, what I'll do is I'll do log.fatal and I'll kill myself. And it's fine, right? Because anyway, it's a simple thing that we're doing. And I'll just do copy of listener and I'll just print listener over here. Done. If I do again, nothing would happen, but I just got printed hello world, which is what is expected over here. Okay, so now listening is done. But now what after listen? What's the second step? This is the first step. So we have started reserving a port for us. Now what's the second step? The second step here is that we want a client to connect. That's really important, right? So what happens is there is a system called accept. The accept system call is a blocking system call. So when you call accept, your program would block at that stage and it would only move forward when some client connects to it. So what I can do is the listener that we created, that, hey, on this port, whenever some client connects, then do something, right? So this is a blocking call. Remember this. So now what we'll do is we'll write the same part over here and just close this off. Okay. So here what we are doing is we have the listener set up. Now we are waiting for the connection to happen. So I'll do listener.accept. This is a blocking call. Now what's the return value of accept? Accept returns me a connection and an error. So I'll accept it in the connection object and an error object. I'll copy paste the error. In case any error, kill myself. But then whatever I got as the connection, I'm just printing the connection at the end because it's the connection that I got, right? Now let's run this. Now let's run this and see what happens. So I have a separate terminal set up for this exact same thing. I'll do go run main.go and my server has now started. Now that my server has started, what I have to do is I have to connect to it. Now because it's a TCP server, I can literally fire a simple curl request. We have not handled HTTP yet, but what I can do is I can fire a simple curl request, because a simple curl request when you setting up an HTTP connection, internally it is also a TCP connection. So curl http://localhost:1729 will actually establish a TCP connection with this server, and then I should see it moving forward. So you saw that here I have go run main.go. It did not kill because it is waiting. It is waiting for that connection to be accepted, right? A client to connect. Now let's see what happens when some client connects. So I'll just hit curl on this, and we saw that it printed in the print I passed connection. It printed something and then it exited, which clearly sees, or which clearly shows that our server is running. It is bind, it is reserving the port 1729. It is listening on it. It is waiting for any client to connect on it. Whenever a client connects, at that point in time, what we are doing is we are printing that and exiting, right? So we just built a very simple TCP server that listens to a particular port. It waits for a client to connect to it. Once the client connects, we are printing that connection and we are exiting, right? So this is a very simple TCP server that we wrote. Now, what's the third step? The third step over here is that once the connection is established, in the curl request, what we'd get HTTP request. So what we have to do is, when a client connects to my server, I would have to read the request. I would have to do some processing, and then I would have to write the response and then close the connection. So that's exactly what we'll do. So again, let's jump to our code and we'll start making the simple changes. So whenever I'm getting a particular connection, let me write a simple function called do, and I'll pass the connection object over here. And in the do function, I will be passing net.connection. I'll accept my connection object, and what it would do is I would want connection to read something. I want connection to write, which is I'll write the response. I'll accept the request, I'll write the response, and then I'll close the connection, right? Okay, now let's see each of the methods parameter. So what is read accepting? Read is accepting a byte array. So obviously you want, like when you are doing read, you want to read the request and store it somewhere, which is what we are doing. So I'll create a byte object, simple. I'll create a buffer of byte, and I can pass in, wait, I'll have to do this, buffer of byte is equal to make, and I'll pass in of byte, let's say 1024. The maximum request or the maximum length of the request that someone can send me is, let's say, 1024 characters or the 1024 bytes, right? So what I'll do is I'll pass buffer over here, right? So this is where what I'm making is I'm now listening. So when the connection is established, I'm making this read call. Now what is this read call? This read call is also a system call, which means it is a blocking call. So when this function is invoked, my process would not move forward over here. It will stop unless, like, until client sends me the request. So once the connection is established, I'm making a read call. So I'm waiting until my client sends me the request. Once the client sent me the request, let's see what read gives me. Read gives me n and error. N is basically the number of bytes that I read and error. So I skip the number of bytes that I read, but if I see any error, like always, I'll just do log.fatal of n. This is just more about, because it is demonstration, I'm just basically killing my process every time I'm seeing anything wrong, right? Okay, but in production, you might do something different. So now that we have read, now what do we want to do? We got the request and then we have to do some processing. Let's say we do some processing, and for us, the processing is more about sleeping. Time.sleep 1 into time.second. So what I'm doing is I'm mimicking a long running process. That hey, it takes me 1 second to do something, right? So I'll wait for 1 second and then I'll write. What do I have to write? What I have to write is the write accepts a byte slice to be written. Now what is this byte slice? Now I can respond with anything, literally anything. I can pass in of byte and say I want to pass in hello world, right? The thing is that because we are making curl request, it's an HTTP request, we would want to send in HTTP response so that your curl understands that it got HTTP response. I can send this as well, but what we'll do is we'll just format it in a beautiful way so that your curl actually renders hello world beautifully. So I'll just send http/1.1 space 200 OK, which is 200 response code /r/n, and then I'll do /r/n. I have to give one more /r/n over here. This is the protocol that we are following. And yeah, we are writing this and then we are closing the connection. So if all goes well, what we should be seeing is when we start the server and we fire the request, we should see hello world in the response. Let's see if we see hello world in the response or not. We fired, we got the request, boom, hello world. And if you see, it took some time to do it because we added that sleep of 1 second. Otherwise it would have responded immediately. So what we just did is we sent the HTTP request. Our server sent the response. So now you can very easily see that the changes that we did over here is you can see that whatever request we are getting, we are capturing it in buffer. You could extract the HTTP URL and then you can write your own fancy stuff that, hey, this is the method, this is what I would want to call, which is exactly how what your web browser does, like your Spring Boot and your Flasks and all. They do exactly this. So whatever you get on the socket, they extract that information and see what method needs to be invoked. Okay, but we'll not go into writing that. But you see how we read, we processed, and we responded, and then we closed the connection, right? Okay, so what's the next step? We did all of this, but few things to note, that the read call is a blocking call. The write call is a blocking call. So when you invoke the read, unless there is something from the client to send to you, you would not be moving forward. So it's very essential that you exactly know when to call the read function. You want to be exactly sure when you're calling the write function. Because if your client is not if your client is not reading while you are writing, then your process is blocked. Right? So you have to be very, 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 very careful. Okay. Now let's see what happens. Now the next step is we want to do this over and over again. Now, if you look carefully, what has just happened is when I was executing this, I started my HTTP server, or rather I started my web server. Let's see it once again. And then when I fired the curl request, what happened is I got the response and my server exited. It exited successfully. There was no error. You could not see any error over here. Your server actually perfectly exited. But is that what our web server does? No. Our web server is continuously running, continuously accepting the request, doing the processing, writing the response. So what we'll do is we will change our code. We'll change our code to do exactly this. So what we have to do is we have to put this in an infinite for loop. Simple. I just put everything in an infinite for loop. So now what would happen? When I fire a request, the request would go, like I fire the curl request, it would come to the server would do that processing, and then it would wait. It would again come back to listener.accept. When it comes to listener.accept, it would start process. It would wait for a client to connect and then do the processing all over again. right? So let's see a quick demo and see how it pans out. So I'll do go run main.go. On the second, I'll pass curl http:// localhost 1729. We got the response, but now you see our server is still running without any problem. I can fire another request. In 1 second, I'll get another response. I fire another request, I get another response. The reason it is happening is because we put except inside the for loop. So what is happening? The control flow of our code is looking something like this. The code entered over here. It is waiting for a client to connect. Once the client connected, it do connection, in which we read, we processed, and we outputted, right? Which is exactly what we did. And once we responded, the connection was closed. It again came back in the for loop, and we did this. It again waited, and then again and again, all over again. So if I would have exited this for loop, my program would have exited because there is nothing more to execute. Which is why typically web servers are typically implemented as infinitely running for loops, right? Now you see how web servers are implemented. Now the next step, we are doing this all over again. But then what's the challenge? Let's hit multiple requests at the same time, and then let's see what happens. So before we do that, let me falsely just add this response to, let's say, 8 seconds. So what I'll do is the processing that I'm doing, let that processing happen for 8 seconds so that we can see the demo of like how things react. So what I'll do is I'll start my server again, go run main.go. In the first client that I have, top right, I'll invoke the curl request. I'll just quickly invoke the curl request. I go at the end, I fire another curl request. Now if we look carefully, the server is doing something. We don't know what we are doing. We haven't added log statement, but my client 1 got hello world, but now it has been very long. My client 2 has not got any hello world. Now it got hello world. Hey, what's happening? I thought we would get response at nearly the same time because we called curl from both the places in one shot, but it did not happen. Let's add some logging statements to understand what is happening. So whenever I'm accepting, so let me write this, fmt or other log.println, waiting for a client to connect. And then when the client is connected, I'll write client connected and all, right? So we're waiting for the client, we say client connected, and we do processing. It does the processing and does not. So I'll just add one more log statement over here. I'll write processing the request. It would give us enough visibility on what's happening. Let's run this. Let's run this and see what happens. I'll just start the server again. Control C. Oh, sorry. I started the server. And now we got the first statement. It is waiting for a client to connect, which is exactly what we wanted. And now I'll fire this. Client processing the request. And when I fire the curl from here, we did not see anything getting printed there. We saw waiting for the client to connect it. Then it returned hello world there. Then it waited for client to connect. And now we would see hello world over here. You see the execution is sequential. Because we waited for 8 seconds, the total execution actually happened for roughly 16 seconds, right? This is why is it happening? Because the for loop that we wrote is happening one after another. So what this shows us is, let me run it one more time so that it just becomes crystal clear that I hit curl over here. I hit curl over here. You see one process getting, one request getting processed. That got responded, and then another process happening. Now after 8 seconds, this would get hello world in response. So the execution is actually sequential, right? This is what is happening. So if I take you through the source code, which is exactly what we wrote, and we can't expect anything else to be done. What we are doing is we are waiting for a client to connect. Once the client is connected, we are doing something. While we are doing something in which we are reading the request, processing it, sending the response. And once that is done, then we are waiting for the client to connect. So the server that we wrote cannot handle concurrent request coming in. The server that we wrote can only handle one request at a time. which is what it shows, because this is precisely what we wrote as a code. This is precisely what a single threaded server is. That on that one server that you have, you are not able to accept multiple requests, because that's what our code is. We have an infinite for loop. We are accepting a client, or we are accepting a connection. Then we are doing some processing, and then we are returning, we are closing the connection, and then the circle continues. So unless and until we come back to this line very quickly, like we want to reach here as fast as possible, but until this function execution completes, we cannot come back over here. That's the thing. That's the thing that we would want to address. So what do? This is precisely where multi-threaded server comes in, parallel processing. So what we can do is, while we are accepting the connection and then we are processing it, our do function, what if we do the do part in a thread? What would happen? So when I'm accepting the connection and I'm doing that processing, what if that doing of or handling the request happens in a separate thread? Once that is spawned into a separate thread, my main thread can go back to the top of the for loop again very quickly and make the accept system call, waiting for it to accept the client, or waiting for the client to make a connection. Won't that work? That's precisely what multi-threaded server does. So the only change that I'll do over here is in Golang, I can create a simple Go routine like this. I can just prefix my statement with Go and would run it as a separate Go routine. Now what would happen? Now if I run this exact same thing as my code, now let's see if we can handle multiple requests at once. I'll start at the server, I did a curl, I came back here, I did a curl, and you see immediately this getting printed that I'm processing the request. And you see the first response getting hello world, and immediately 2 seconds later we see second request getting hello world. We did not have to wait for 8 seconds for second thing to come out. So here we see that how multiple requests, now our server can handle multiple requests at once. The magic was that we wanted to invoke accept as soon as possible. We did not wait for the processing of the first request to complete before we could go to accept, which is why what we did, we spawned it into a separate thread, which is precisely what multi-threaded server does, right? So let me once again show you the demo so that it becomes crystal clear. I'm invoking curl. You see the message getting printed. I'll invoke curl over here. You see message getting printed. Both the requests are being handled concurrently by my server in 2 separate threads. First request responded, and now the second request would respond. That's the beauty of this implementation. This is precisely what multi-threaded server does. And this is how, be it any programming language, be it any framework that you see like Gin framework or Flask or Gunicorn or any web server that you write, which can handle multiple requests, which are multi-threaded web servers or multi-threaded TCP servers. This is precisely what they do. This is precisely what they do is when they are waiting. So their main thread is constantly just in this for loop, waiting for a client to connect. Right? Whenever a client connects, they spin out or they spin off a thread to handle that request independently. And then it waits again. They spawn out another thread and then it waits again, and so on and so forth. This way, any multi-threaded server handles multiple incoming requests concurrently. Right? Okay. There is another class of TCP servers which are single threaded, but they can still handle multiple requests. I have covered it in my Redis internal course. In case you are interested, you can check out, the link is in the description. So, but here our focus was to understand multi-threaded servers. So again, just to reiterate, there is also a category of single threaded servers which handles multiple concurrent TCP connections. The way they do it is little internals. It's part of my Redis course, so I won't put it out in this video. But now you see what happens, like how you can build your own multi-threaded web server. Right? This is precisely what happens behind the scenes, and this is how you build multi-threaded web server. So just understand, like here, the way we went for it was that we understood what each system call did, like accept, read, write. We knew they were blocking, which is why what we did is, as soon as we knew that our server would not be able to accept the request unless we invoke the accept system call, so we waited. So what we did, we did it in the main thread. while as soon as a client connected, we forked out a thread specifically for that request to be handled, which is exactly what is happening. So for every client that is connected, we are forking out this request into a separate thread, and then it does its own read and process, and like read, processing, write, and out and closing, right? This is the idea. This is what every single web server does. So now here you start seeing some problems. Problem number one. What if a large number of clients connects to this server? When a large number of clients connect to this server, what would happen? If whenever a client is getting connected, we are immediately invoking a new thread to handle that particular request. So when a large number of clients connects to this server, what would happen? For every request, a new thread is spun up. Thread overload. Or rather, there would be huge number of threads on my machine. That's not good. Which is where there are a bunch of optimizations that needs to be done, which all multi-threaded server does. First of all, you typically don't spin up a new thread for every request. You have to limit the maximum number of threads which your server would be spinning up, because a server is not just accepting the request and handling it. The handling part itself would require multiple threads, because there is this hardware limit of the amount of memory in the CPU and the resources that you have. You cannot just spin up infinitely large number of threads over there. So which is where you would have to limit the maximum number of threads that you can invoke. So that's what it does. Now for you to do that, there is something called as a thread pool. What would you do is you would spin up a thread pool that contains, let's say, 1000 threads. And whenever you need the thread, you go to the thread pool, read the thread, do the processing, and then put the thread back to thread pool. This way you limit the number of threads that your process would ever have. Then you would need connection timeout. What if a client is connected? You are waiting for something. What if that client never sends you the request? You cannot just infinitely wait, because you are just hogging up a TCP connection. So what you need a connection timeout. So whenever a new thread is forked out, there is a timeout associated with it. That if my thread does not respond, or if my client does not respond in that much of time, I would kill that connection. Right? So that's what happens with connection timeout. And the final one, there is something called as a TCP backlog queue, which is an operating system level setting that determines how many connections you would want to keep in your backlog. Right? Just Google about it. It's quite an interesting field to explore. So yeah, that's how you create a multi-threaded web server. I hope I was able to spark some interest on the internal side of things. The idea being that you just apply a basic first principles while building anything, and you can literally build anything around it. Right? So yeah, now you understood what system calls are, why are they blocking, how multi-threaded web servers are even conceptualized, and what other factors you need to consider to improve the performance of any multi-threaded web server. Now, beat any web server, Tomcat, you pick Spring Boot server, whatever they are using, Gunicorn, Nginx, all of them, any server that is multi-threaded, you can literally open their source code and you can see something very similar to this, really very similar to this. And this is what the beauty of first principle thinking is all about. So yeah, that's all what I wanted to cover in this one. I hope you found it interesting. Hope you found it amazing. That's it for this one. I'll see you in the next one. Thanks, Eta.